In classification, we've seen that you can use accuracy, the fraction of correctly classified samples, to measure model performance. However, accuracy is not always a useful metric. Consider a spam classification problem in which 99% of emails are real and only 1% are spam. I could build a model that classifies all emails as real. This model would be correct 99% of the time, and thus have an accuracy of 99%, which sounds great. However, this naive classifier does a horrible job of predicting spam. It never predicts spam at all, so it completely fails at its original purpose. The situation when one class is more frequent is called class imbalance, because the class of real emails contains way more instances than the class of spam. This is a very common situation in practice and requires a more nuanced metric to assess the performance of our model. Given the binary classification task, such as our spam email example, we can draw up a 2x2 matrix that summarizes predictive performance, called the confusion matrix. Across the top are the predicted labels, down the side the actual labels, such as you can see here. Given any model, we can fill in the confusion matrix according to its predictions. In the top left square, we have the number of spam emails correctly labeled. In the bottom right square, we have the number of real emails correctly labeled. In the top right, the number of spam emails incorrectly labeled, and the bottom left, the number of real emails incorrectly labeled. Note that correctly labeled spam emails are referred to as true positives, and that correctly labeled real emails as true negatives, while incorrectly labeled spam will be referred to as false negatives, and incorrectly labeled real emails as false positives. Usually, the class of interest is called the positive class. As we are trying to detect spam, this makes spam the positive class. Which class you call positive is really up to you. So why do we care about the confusion matrix? First, notice that you can retrieve accuracy from the confusion matrix. It's the sum of the diagonal divided by the total sum of the matrix. There are several other important metrics that you can easily calculate from the confusion matrix. Precision, which is the number of true positives divided by the total number of true positives and false positives. It is also called the positive predicted value, or PPV. In our case, this is the number of correctly labeled spam emails divided by the total number of emails classified as spam. Recall, which is the number of true positives divided by the total number of true positives and false negatives. This is also called sensitivity, hit rate, or true positive rate. The F1 score is defined as 2 times the product of the precision and recall, divided by the sum of the precision and recall. In other words, it's the harmonic mean of precision and recall. To put it in plain language, high precision means that our classifier had a low false positive rate. That is, not many real emails were predicted as being spam. Intuitively, high recall means that our classifier predicted most positive or spam emails correctly. Let's now compute the confusion matrix along with the metrics for the classifiers we trained on the voting data set in the exercise. We import classification report and confusion matrix from scikit-learn.metrics. As always, we instantiate our classifier, split the data into train and test, fit the training data, and predict the labels of the test set. To compute the confusion matrix, we pass the test set labels and the predicted labels to the function confusion matrix. To compute the resulting metrics, we pass the same arguments to classification report, which outputs a string containing all the relevant metrics, which you can see here. For all metrics in scikit-learn, the first argument is always a true label, and the prediction is always the second argument.